In the last few videos, we have learned how to write the chemical potential for a gas and for a liquid in an ideal solution. These are the expressions. For a gas, the chemical potential is equal to the chemical potential at 1 bar, standard state, plus a correction from the fact that the partial pressure of the gas might not be 1 bar. And then for an ideal solution, for the liquid in an ideal solution, the chemical potential is going to be equal to the chemical potential when that liquid is pure, plus a correction for the fact that when you have it in a solution, it will not be pure. Now, we were able to write this chemical potential from that of a gas using Raoult's law, which we're going to redraw right here. So Raoult's law essentially tells you how the vapor pressure of a substance changes when you mix it with something else. Okay, so we have a substance A in solution, and again, what we're trying to measure is what the vapor pressure is of that substance on top of the solution as a function of the mole fraction of A in the liquid phase, right? So what we're doing here is adding some component B, and that alters the vapor pressure of A on top of that mixture. And what we actually know is that this is a straight line. Okay, so that's Raoult's law that tells you that the vapor pressure of that component is going to be the regular proportional to the mole fraction of that component in the mixture, and then the proportionality constant is just the vapor pressure of A when it's pure, okay, which is this value. Okay. The same thing would happen for component B, which in this case would run opposite. Okay, component B will go from 0 to 1, and you will have a graph that looks like this if B is more volatile than A. Okay. All right, so again, using this law, we can go to this chemical potential and then rewrite the chemical potential in the ideal solution. Now, what does it mean for a solution to be ideal? When we're thinking about gases, one of the conditions for ideality in gases is that the molecules of the gas are not interacting with each other. And this is reasonable to approximate low pressures, because at low pressures, the gas molecules are significantly removed from each other, and they're rarely going to interact with each other. So that approximation is fine. Now, when you have a solution, the idea that the molecules will not see each other falls apart, because in a solution, the molecules are on top of each other. They're interacting with each other. So then the condition for ideality changes a little bit with respect to the gas phase. In this case, what we say is that the solution will be ideal if the interactions of A with B are very similar to the interactions of A with A or B with B. Okay, so that when you mix them, there's no change really to the interactions that you already had. All right, so as it turns out, this condition for ideality is very rarely satisfied. It is satisfied when the two molecules that you're mixing, A and B, are very similar to each other. For example, when you mix benzene, which is this molecule, and toluene, which is this molecule, they do form an ideal solution because the interactions of toluene with benzene are very similar to the interactions of toluene with another molecule of toluene, or benzene with other molecules of benzene. Okay, but if you mix, for example, water and ethanol or water and benzene, then you will no longer have an ideal solution. Okay, and you can actually see that you don't have an ideal solution because it turns out that Raoult's law is not satisfied, right? So if you were able to measure these vapor pressures as a function of mole fraction, you will see that you actually have deviations from ideality, and you will see that, again, these laws are now just going to be limiting laws, and in reality, you're going to have something different. Okay, so we draw these now as dashed lines. And again, what you see in reality is that this is going to be something like this. You're going to have deviations, okay, like that, and like that. Okay. In this particular case, notice that we're actually drawing the lines, the actual lines, the experimental lines of the components of the mixture with a vapor pressure that is higher than what Raoult's law predicts. That is called a positive deviation from Raoult's law. And the reason that you might have this type of added vapor pressure is that when you mix A and B, the interactions of A with B are more repulsive than A with A and B with B, and that means that there's an increased tendency for the molecules of A and B to escape into the gas phase because the environment in solution is not as attractive, so a little bit more repulsive than when you have the pure liquids. Okay, so that is what leads to a positive deviation. Analogously, you will have a negative deviation in which when you actually draw the lines of the vapor that you measure in the experiment, they would fall below what you actually have for Raoult's law. Okay, so this would be a negative deviation. Okay, that one and this one. Okay, so negative deviation, notice that the vapor pressures fall below the prediction from Raoult's law. And the origin of that deviation would be that when you mix A and B, the interactions of A with B are actually stronger. They're more attractive than the interactions of A with A and B with B. Okay, so in that case, you will see this negative deviation of the vapor pressures with respect to Raoult's law predictions. All right, so in the next videos, what we're going to explain is how then we write the chemical potentials for solutions that have these deviations from ideality. That is that expression we have derived assuming ideal behavior, but again, most cases you're going to have this, right? So the question is, how do we actually continue to write these chemical potentials, which are extremely important for the rest of the chapter and when we study chemical equilibrium, okay, when you have deviations from ideality.